What specific problem does the new method or algorithm aim to solve regarding traditional reinforcement learning paradigms?
The new method, termed the Causal Reflection framework, aims to address the fundamental limitation of traditional reinforcement learning (RL) paradigms, which often rely on spurious correlations rather than true cause-effect relationships. This framework introduces a temporal, action-based causal function that captures both linear and nonlinear causal relationships in dynamic systems, enabling agents to reason about delayed effects and temporal dependencies. Additionally, it incorporates a perturbation factor, delta, to model the sensitivity to initial conditions and structural breaks, which traditional RL methods typically overlook. By integrating causal reasoning directly into the learning process, the framework enhances the agent's ability to generalize beyond training environments and adapt to changing conditions. Ultimately, this approach seeks to create more interpretable, robust, and generalizable AI systems capable of functioning effectively in complex real-world scenarios.
How does the proposed method or algorithm work? Illustrate step by step, particularly focusing on the temporal action-based causal function and reflect mechanism.
The proposed method, causal reflection, operates through a structured framework that integrates causal reasoning with reinforcement learning. First, it utilizes the temporal action-based causal function which maps the current state S_t, action A_t, time T_t, and a perturbation factor, delta, to predict a future state S_t plus k. This function accounts for both immediate and delayed effects of actions, allowing it to model complex, non-linear causal relationships in dynamic environments. Next, the reflect mechanism is invoked when there is a discrepancy between the predicted outcome, hat S_t plus k, and the observed outcome, S_t plus k obs. This mechanism analyzes the causal tuple to generate hypotheses about potential causes for the mismatch, such as unmodeled perturbations or shifts in causal dependencies. By formalizing this reflection process, the framework enables agents to revise their internal causal models based on real-world feedback, enhancing their adaptability and interpretability in changing environments.
Can you come up with a simple yet illustrative example on the inner workings of the proposed algorithm, specifically showing the application of the perturbation factor $delta$ in a dynamic context?
An illustrative example of the proposed algorithm's inner workings can be seen in an ecological model where an agent predicts animal behavior based on environmental actions. Suppose the agent takes an action, such as introducing a new food source, A_t, at a specific time, T_t. The expected outcome is that animal activity increases, leading to a future state, S_t plus k, of higher population density. However, an unexpected perturbation, delta, like a sudden lightning strike, occurs, which alters the habitat and creates a chaotic effect on animal behavior. The causal function incorporates this perturbation, allowing the agent to model how the initial action's impact is amplified or dampened by the perturbation, resulting in a different future state, S_t plus k. This dynamic context illustrates how the perturbation factor enables the agent to adapt its predictions and refine its causal understanding in response to unforeseen changes in the environment.
What are the theoretical or practical benefits of using the causal reflection framework over traditional causal reinforcement learning methods?
The causal reflection framework offers significant theoretical and practical benefits over traditional causal reinforcement learning (CRL) methods by addressing the limitations of static causal structures and enhancing the modeling of dynamic, time-varying relationships. Unlike conventional CRL approaches that rely on fixed causal graphs, our framework incorporates a temporal action-based causal function that captures evolving causal dynamics, allowing agents to adapt to non-stationary environments. Additionally, the inclusion of a perturbation factor, delta, enables the framework to model nonlinear effects and sensitivity to initial conditions, which are critical for understanding complex systems. Practically, this framework enhances explainability by allowing agents to generate structured causal hypotheses and actionable insights, moving beyond mere correlations to provide deeper causal understanding. Overall, causal reflection shifts the focus from policy optimization to causal understanding, positioning agents for improved generalization and interpretability in real-world applications.
How was the method validated or tested? Discuss the proposed validation strategy and the metrics used to evaluate the agent's performance.
The proposed validation strategy for the causal reflection framework involves developing a benchmark suite of simulated environments that feature known, dynamically changing causal relationships. For instance, a simulated economic system could be used to model government intervention as a perturbation, delta, that alters the causal link between interest rates, action, and inflation, state. The evaluation of the agent implementing causal reflection focuses on its ability to identify the active causal graph and how quickly and accurately it can detect and update its causal model following a structural break. Additionally, the agent's performance will be assessed based on its effectiveness in predicting future states, specifically minimizing prediction error after perturbations. This approach emphasizes the importance of causal understanding over traditional reward metrics, aiming to ensure that the agent can adapt to and accurately model complex, non-stationary environments.
What results were achieved with this new method? Can you specify any findings that demonstrate effectiveness in dynamic environments compared to previous models?
The causal reflection framework achieved significant advancements in modeling dynamic environments by introducing a temporal action-based causal function that captures both linear and nonlinear causal relationships, addressing the limitations of traditional reinforcement learning (RL) and causal reinforcement learning (CRL) models. Specifically, it incorporates a perturbation factor, delta, that allows the model to account for unexpected influences and structural breaks, enhancing its sensitivity to initial conditions and enabling it to adapt to non-stationary environments. The framework's ability to generate structured causal hypotheses and explanations through the integration of large language models, LLMs, further demonstrates its effectiveness, as it provides actionable insights rather than mere correlations. Additionally, the proposed validation strategy emphasizes the agent's capability to quickly and accurately identify active causal graphs and predict future states following perturbations, showcasing its robustness in dynamic settings. Overall, these findings indicate a marked improvement in generalization, interpretability, and alignment compared to existing models that often rely on static causal structures.